Welcome to the TEEP podcast, brought to you by the State Energy Conservation Office and Energy. We present the latest in industrial energy efficiency in 15 minutes or less. However, this week we've had holidays, so there has been really no past events for the last 2 weeks, and still there's probably going to be very little in the next 2 weeks either. So instead, we're going to bring to you a special edition. We have an interview with Dr. Michael Harold. Dr. Harold is professor of chemical engineering here at the University of Houston. He is a recognized leader in catalysis and reaction engineering. Oh, and I should mention, we've been neighbors for decades. Our kids went to school together. So if it sounds a little bit personal at times, that's because I've known Mike for quite a few years. He's a friend. So today we're going to, first of all, Mike, introduce yourself to us.
Hi, Gary. Thanks for the opportunity to meet with you. Yeah, we've been friends for quite some time and neighbors, so this is a different kind of venue to get together.
Absolutely.
So, yeah, my background is chemical engineering. Did my undergrad at Penn State, then went to actually University of Houston for a PhD.
Wow.
Left Texas back in the 1980s. Didn't think I would return, but I did. Between when I left and when I returned, I worked at the University of Massachusetts, joined academia, started a research group at UMass Amherst, as they call it. My expertise throughout the years has been catalytic reaction engineering, or CRE for short. Started that at UMass Amherst, stayed there for about 8 years, and decided to move to industry, which was kind of unconventional for an academic. I wanted to get some industrial experience and moved to DuPont Company in Wilmington, Delaware, their corporate research.
I've heard of them, big company, a lot of interesting things going on there.
Yeah, actually still the oldest corporation in the United States.
Wow,
so,
yes.
I believe the late 1700s. But I joined DuPont at the time because they had a world-class group in chemical reaction engineering, and I reached out to them, and they were keen on my joining, so I did that and spent the next 7 years of my career in DuPont in different roles, including a chemical reaction research role.
That produces a lot of great experience, I'm sure, to actually be in industry and see what's required there.
And when I reflect back on making that decision, I wouldn't have changed a thing because it exposed me to some of the real challenges in the chemical industry and got me to thinking differently about research and how it can be used in the shorter term effectively, not just a long-term kind of exercise.
Fantastic. And then you decided to come back to the University of Houston.
Yeah, for a myriad of reasons. I moved back to University of Houston. They had a department chair opening in chemical engineering, so I returned to my alma mater.
Well, that's an opportunity you can't just give up. So
yeah.
That was fantastic.
That was turn of the century, about 25 years ago, and I've been at U of H ever since.
Oh, fantastic. And you've had a lot of great grad students come through your department as well, and some mature students as well.
That's right, including yours truly, right?
Yeah. Full disclosure, Mike was my advisor for my PhD program that just finished last year. But that's what we're not talking about that today. We're one of the reasons we brought you in today is because of your electrified steam methane reforming process and catalyst that you've developed here. Very exciting. We mentioned it in our last newsletter. Tell us more about this, because it sounds like both a great electrification process, and you discovered some energy efficiency issues there as well. Tell us about this.
Sure, yeah. Methane steam reforming is the main way to make hydrogen in the chemical and fuels industry, and hydrogen is viewed as an important molecule and it has always been. It has some challenges, certainly, but a lot of opportunities as an energy source. Now, the way it's made conventionally is methane, CH4, reacts with water to make hydrogen and carbon oxides. The hydrogen that's made is purified and used in a variety of applications. Now, the way it's made conventionally is a so-called box furnace, where temperatures go up to on the order of 800 centigrade in order for these two reactants to get together and form hydrogen catalytically. That box furnace, by its name, involved the burning of fuel, usually natural gas, to generate those high temperatures. The high temperatures are needed to make that conversion happen. Now,
these are massive units. I've been to a number of them myself, and I think the average person probably doesn't appreciate how big they are. Fortunately, most of our audience here is chemical engineers who've seen these.
That's right. So the heat that's generated by that combustion drives the steam reforming reaction. A few years ago, we decided, in collaboration with a couple of my colleagues in chemical engineering, in a project sponsored by Shell, look into a different way of bringing the heat in to do the methane steam reforming. And this involves electricity. Now, you might ask, well, why would you do that? A couple different reasons. And the one I'll focus on today is efficiency. As Gary, you pointed out, when you burn a fuel and generate a high temperature, there's this complex process of transport of that heat into the reaction zone, and that leads to a number of inefficiencies. So we wanted to examine the possibility of bringing the heat in a different way.
Yeah, these furnaces, as many people know, are very, very complex, combined with the radiant section for the reaction tubes exist, the convection section where you're trying to recover some of this very high temperature gas as well, with steam generation, the whole thing. So electrification actually sounds like a simplification as well.
Yeah, I mean, if you think about your kitchen, many of us have toasters or toaster ovens, and we wanted to try to see if we could use that approach to heating applied to steam methane reforming. So if you look inside your toaster, you plug it in and you turn it on, you see the glowing wires that are doing the toasting. Basically, we were asking the question, could we use wire heating as a way of doing this reaction? And that's where the challenge was posed to my student.
So how did all this work out?
Very well. So if you can imagine these wires that you see in the toaster oven, we would coat the wire with a catalyst layer, a coated wire, apply a voltage across the wire in a reactor, flow methane and steam over that coated wire. And so when you think about it, the voltage that you're applying is generating a hot wire, which is in direct contact with the catalyst, and that's where all the action happens. Compared to a furnace where you're burning a fuel outside tubes that are filled with catalyst, which again presents some potential inefficiencies. This way, we're bringing the heat directly to the catalyst by putting the catalyst on top of the hot wire.
Okay, so I gather it was better than just a one-to-one relationship. Okay, full disclosure, I've seen the results myself, so and they look pretty darn good. Do you have any efficiency calculations? I know it's difficult on this small scale to really do it.
The best thing we can do at the small scale that we work in, I mean, ultimately you want to make that macro system efficiency comparison.
Well, we're going to have to do that.
Yeah. Now, what we did was pretty straightforward. We compared directly the coated wire electrically heated, as I was mentioning, to the same wire coated with catalysts, snipped up, put into a tube, and then heated externally.
Okay, that's and if you do external heat, what kind of results do you get compared to actually electrified?
Doing that direct comparison, so as close as we can make it an apples to apples comparison, there's a range of conditions where the electrically heated wire outperforms the conventional quote unquote approach that we were trying to mimic on the small scale that we work in our lab. That comparison involved measuring how much or what fraction of the methane reacts to make hydrogen in both cases. And for the same conditions, the electrically heated wire outperformed the conventional system in a marked way, which was somewhat surprising to us.
Okay, so you got a lot more activity out of the electrified catalyst.
Yeah.
Is that an electrochemical effect, do you think, or is it magnetism, or have you come to a conclusion yet?
We're looking at a variety of different explanations. You're mentioning magnetism. I didn't mention that the wire is coiled. So if you think back into your university physics, a coiled wire with a current passing through it generates a magnetic field.
Yes.
And we don't know yet whether that generated magnetic field is having any effect on the catalytic reaction. What we're currently hanging our hat on is an electrochemical enhancement that gets into some details about the conductivity of the electrons through the catalyst layer.
Okay, that sounds pretty complex, and I'm sure it's going to spur many years of research going on. Any progress on getting this commercialized? Any of the majors looking at it with you?
Well, Shell has supported the research. That project's coming to an end, and we have filed a non-provisional patent to the U.S. Patent Office, and that is under review currently.
Okay. It sounds like I've got a different hat that I've got to wear for that. I know people in the industry, which is fantastic, and we can certainly check in our network on it. So that all sounds very promising. Electrified steam methane reforming, love it. What else is new in catalysis? Where do you think, well, electrification, electrochemistry, you think there's a strong future in that? Is it more of the same compared to just thermal chemistry these days?
There's more interest in it nowadays for reasons including efficiency. In the case of methane steam reforming and similar reactions like steam cracking to make ethylene, as an example.
Okay.
Electrochemistry, where one deliberately uses the electrons in the chemical reaction, has been a focus of study in chemistry for decades. It has led to some commercialized processes. Some believe that that is an area of growth.
Okay, we had Omar on earlier, and he was certainly talking about that. And
Right.
see, there's a lot of promise on that. So, anything else you want to add before we wrap up our session here today?
Nothing other than thank you for the opportunity to talk to you, Gary, and I applaud your effort here in leading the energy efficiency initiative at the University of Houston.
Okay, well, thank you very much for coming in to talk to us this week. This podcast is brought to you by the State Energy Conservation Office and the Media Lab here at UH. I'm Gary Gildert, and we'll be back next week with a full episode, not so much of recaps, but we'll be talking about some future events and a fascinating article more about hydrogen.